Thank you. Fine. So we start with a new topic today. Probably the class might be a little lengthy. Anyway, if you have any questions, I will request you to ask on the spot. I mean, whenever you have any question, please do ask at that time. So we start with small disturbance stability. So the prerequisite for understanding this small disturbance stability is the swing equation. We have already completed the slide of swing equation. So now we start with small disturbance stability. All right. So before that, let's go through some of the definitions and some assumptions. So small disturbance stability or steady state stability refers to the ability to remain in synchronism when subjected to small disturbance. Okay, that means whenever there is a small disturbance, it is very obvious that your system will deviate from the equilibrium. But if your system has the ability to regain that equilibrium point, then we say that the system is stable. And small disturbance signifies that, I mean, if you recall the first slide, first slide that we learned, over there was a classification of the type of disturbance. So over there we saw that there are two categories of disturbance initially, which were small disturbance and large disturbance. So based on that, we are only dealing with small disturbance in this particular slide. We are not talking about large disturbance. We are only dealing with small disturbance. Okay, so disturbance may disappear within a very short time, which is a pulse type, or last for a longer duration. Okay, so it depends on the type of the disturbance. If the disturbances disappear, the motion of the system is assumed to be free. Okay, is assumed to be free. Let us try and understand what does this mean. Okay, we'll come to that. And stability is assumed if the system regains its original equilibrium. Remember, not any new equilibrium, it has to regain its original equilibrium. So it is easier if we explain from the term of a pendulum, swinging pendulum. So that was the example that we took. So initially, this is where is your pendulum. Okay, so what it says that if you apply a small disturbance, so you apply a small force over here, and then the force is removed. Okay, say because of this force, your pendulum somehow came up to this position, but your force was removed. Then what will happen? This pendulum will keep on swinging in the absence of the external force, and finally again it will reach at this original equilibrium position. So once the force has been removed, the motion of the pendulum is assumed to be free. That means it is the natural motion of your pendulum, the natural swinging of the pendulum. Okay, there is no external effect anymore. The external effect or the external force F, after the removal of that external effects, if your system swings or is in motion, then we say that that is the natural motion of the system, or the motion is said to be free. And if you remove the force, if you remove the external force, your system will always come back to its original equilibrium. We studied that even if your system reaches a new stability, a new equilibrium position, still then your system is stable. But that scenario takes place when you do not remove the force, when you do not remove the external disturbance. Okay? In that case, there is a possibility of reaching a new equilibrium. But if you remove the force, if you remove the external disturbance, then definitely your system will always come back to its original equilibrium position. Okay, so for a linear system, study of the characteristic equation can be employed to determine the stability of such scenario. Okay. What is our system? The system we had, the swing equation that we had, was that linear or non-linear? Any idea? Those who are over here, I know the response will be less, but still, if you want to respond. So the expression that we had, why do you say it's a non-linear?
So d
I'm not saying your
square
answer is.
theta.
Derivation does not make a system linear or non-linear. Derivation is not that significant in linearity determination. So your answer is correct. It is definitely non-linear. But the question is, why is it non-linear? Do you remember the swing equation?
Yes, sir.
Okay. So in that swing equation, Okay, if you remember the swing equation, then in that swing equation, okay, sorry, I lost my screen. Wait, just a second. In that swing equation, on the right hand side, we had some expression like this, Pm minus Pe, and on the left hand side, we had some, I forgot, it was d squared delta by dt. Then there was some h term, probably, right? Some term was there. It was something like this, right?
So on the right side there was half omega
D
ms.
squared D.
Okay, some constant was there. Okay, fine, half omega s. Okay, let's recall. Okay, let me write the entire equation. Let me see the equation and let me just write the entire equation. It will be easier. Okay, so the expression was, so let's me write over d squared delta by dt. This was equal to omega s by twice h. So this was equal to omega s divided by twice h into Pm minus P, right? This was the expression, isn't it? Is it okay?
Yes, sir.
So this was our swing equation. What was the expression of Pe? It was P max sine of delta, right? So this was my
Max sine
expression.
delta by xt, sir.
No. P max
Oh,
is
sorry.
equal
P max sine
to
delta.
AB by x1. Okay, fine. So this was my expression. So now tell me, is this expression linear or non-linear?
So non-linear.
How can we say that?
So there is a sine delta term.
Right, very good. So in this particular expression, the variable is this particular guy, that is delta. This is my variable. And over here, we see that sine is a function of that specific variable. So presence of this sine or cos on the variable that we are talking about, I mean, if there is a variable, then that makes our system non-linear, okay? Over here, we see that for a linear system, okay? So for a linear system, we can study the characteristics equation and then we can determine, I mean, yeah, this thing you have covered, that location of poles and zeros, right? You have covered this type of scenario that based on the position of poles and zeros, we can determine that whether the system is stable or unstable. But that is only applicable to linear system. And the problem is our swing equation over here is non-linear, okay? So let's keep on going. So in this lecture, it is assumed that the actions of the
Sir.
automatic voltage, yes.
Sir, can you please repeat why it is non-linear?
Okay. So in this swing equation, there is only one variable, and that variable is delta. So if you have a sine function of that specific variable, then your output will be something sinusoidal. Definitely there will be some constants multiplied, but based on that, your output will be something sinusoidal. So whenever you have a sine function or cos function, and within that sine and cos, if you have the only variable that we have, or if there is any variable, then this presence of sine or cos makes your entire system non-linear, because this is the sinusoidal curve, this is the cosinusoidal curve, right? Both of these are what, linear or non-linear?
Non-linear.
Non-linear, definitely. So if I have the
Yes, sir.
presence of sine or cos, and if within that sine or cos we have a variable, then my entire system becomes non-linear. Okay.
Yes, sir.
Okay. So in this lecture, it is assumed that the action of the automatic voltage regulator and governor are inactive. The same assumptions that we assumed for our swing equation as well. Okay? So the same assumptions are still valid in this particular problem. So as we see, this was basically the definition of what is the meaning of small disturbance stability. So that's done. This was the type that whether, I mean, your disturbance will disappear within a short time or it will remain for a long time, something like that. This point we discussed. This is applicable only for linear system. This is my assumption. So this point is the only important point over here so far, because if somehow we can make our system linear, then we can apply the characteristic equation. We'll see what is the characteristic equation. This will come, don't worry. So first thing is we need to make our system linear. This is my first target in this slide, in this presentation. So first of all, my system has to be made linear. Once I have made my system linear, my second target will be to find the characteristic equation. If I can satisfy both of these things, then I can determine whether my system is stable or not. And these are the answers that we'll try to look throughout this presentation. So moving forward, okay, so this was the very expression that we dealt with. This was the same SMIB that we considered. So we have a generator with E dash, then we have the internal reactance of the generator as XD dash, then VG is the terminal voltage of the generator, V is the infinite bus voltage, ZL is the transmission line uh, impedance, and ZS is the local impedance. All of these things we already know. This is the swing equation just we saw before, that is d square delta by dt square is equal to omega s by twice h pm minus p. All of these things we know. So if you just slightly change sides, we get twice h by omega s d square delta by dt square is equal to pm minus p max sine delta. And we concluded that the presence of this particular thing makes our system unstable. Okay, so any question until now? I hope no. These are still the basic things. We have not studied anything new. Now we start something new. That is, we'll try to get the linearized swing equation model. So let's see what happens. So first of all, what we do, we replace delta by del naught plus del delta. Can anyone tell me what is delta naught? What is delta naught?
Sir, initial rotor
Steady
angle.
state.
I mean,
Uh,
both of the answers are correct, but in a slightly twisted way. The answer is delta naught is actually the steady state rotor angle. That is represented by delta naught. You can also say this is the initial delta naught provided you have some disturbance. So if you introduce some disturbance, before the introduction of disturbance, whatever delta value we had, that is my delta naught. So you can say both as it is my initial delta naught or this is my steady state rotor angle. Okay. And
so
this
what
is
did
the
you say about the initial, if we introduce
okay.
some disturbance before?
Right. So say your machine is running, right? Your generator is running. There is no disturbance. It is running in steady state condition. At a particular time, you provide some disturbance. So before the application of disturbance, whatever rotor angle you had, that can also be termed as my initial rotor angle, and that is same as delta naught. So same thing, initial delta naught or initial rotor angle or a steady state rotor angle, both of them signify the same thing. Is it clear?
Yes.
Okay, fine. And this delta naught is my disturbance. Okay. I mean, this is the change in the delta angle, or this is the change in the rotor angle that takes place because of the application of disturbance. So in short, I wrote disturbance, but in reality, what is this actual thing? If you have some sort of disturbance, then there is a change in the rotor angle, and that is represented by del delta. Okay. Okay, so I still have my original swing equation. So what is my target now? Wherever I have delta, now I will change it by delta naught plus del delta. So initially I see that over here I have got delta. So I change it to delta naught plus del delta. Then Pm minus Pmax, sine becomes delta naught plus del delta. Nothing complicated. Now what we do? Now we divide this expression. So we had delta naught plus del delta. So first of all, we just take delta naught. So we have got twice h by omega s multiplied with that. So this is the first expression for just delta naught. Then we have got del delta. So same thing again, twice h by omega s is multiplied. So we have d squared delta naught by. So we just simply separate the expressions. Okay, nothing complicated. Then Pm minus Pmax. Then we got sine. How did we come up with this particular line? This should
Sir,
be easy.
sine A plus B formula.
Right. So sine A plus B, we apply some trigonometric formula. Okay. So sine A plus B gives you sine A cos B plus cos sine B. All right. Now, what is the nature of this del delta? This del delta is my small disturbance stability, right? I mean, this is small disturbance. So how small this has to be? So let's try and understand. Okay. Tell me something. What type of curve is this?
Sir, cos curve.
Okay. Cosinusoidal curve. Very good. So if this is my del delta, then this is my cos del delta. So if del delta is small, so if del delta is small, then where will your del delta reside? I mean, where will it be? Okay, let me give you the options, then the question will make much more sense. Tell me, in which region in this del delta axis will your del delta be? Will it be somewhere over here, or here, or here, or here, or here? Where do you think your del delta will be? I have got
I mean,
1, 2, 3, 4, 5, 6, 7 regions. So tell me, in which region do you think your del delta will be if it is very small?
sir, in region 3.
Is it like all of you that it will be in region 3? See, if you don't understand, you have to ask. Okay. If you do not ask, I will assume that you understood. Okay. So del delta, a small del delta means that it will reside in region 3. That means it will stay in this particular region. So if it stays in this particular region, then cos del delta can be written as what?
Sir, cos 1.
Very good. So it can be written as 1. Now let's say, let's remove this.
Sir, can you please explain this part again?
Which part? Positioning of del
Sir, how
delta,
is
or
cos?
hmm,
Yes,
how
sir.
is?
Positioning of del delta, and also how is cos del delta is equal to 1?
Control Z কাজ করে না. Okay. Let me draw again then. So my curve was something like this, right? Sorry. Okay, it was something like
Sir,
this.
how do we understand that what region should we take for a small disturbance?
So del delta, what is the value of del delta at this particular axis? Tell me. In the y-axis, along the y-axis, what is the value of del delta?
0.
Very good, 0. So you said that del delta is very small. So if you are in somewhere over here, your value will be what? Quite large or still small?
Large, 2 pi almost.
Right, definitely. So when I'm saying that del delta is very small, then we can easily conclude that del delta will reside in region 3, isn't it?
Yes, sir. Yes.
Is the first portion clear, right?
Yes, sir.
The second question was, if del delta lies in this region 3, that means what is the value of your cos del delta? You are talking only about the
1.
small region.
Yes, sir.
In this small region,
Yes, sir.
so cos del delta becomes 1. Clear?
Yes, sir.
Okay. Now let us take another scenario. Now assume you have got this curve. So what is this curve now?
Sine
Sinusoidal.
curve.
Sinusoidal curve. Very good. So again, del delta is small. So positioning of del delta will still be in region 3. There is no doubt about that. So if now del delta is in region 3, then sine del delta, it will be equal to what?
0.
0. 0.
Will it be 0? Let's try and understand. So we said that del delta is very small. So say, so you are talking about sine. It is, say sine 0.01 is equal to how much?
0.01 কাছাকাছি।
Right. 0.01. So if you have sine minus 0.01, this is equal to what?
The sine of del delta will be equal to del delta.
Right. Sine of del delta will be equal to del delta. This time you cannot take it as 0 because you have to include the effect of both positive and negative values. The problem that you did not have in case of cos. Is it understood, everyone?
Yes,
Sir,
sir.
that means we are considering the angles in radian, right?
Yeah, you can take it in radian, degree, doesn't matter. All of this will give you the exact same result.
Oh, okay, sir.
Sorry. Yeah. Is it okay?
Yes, sir.
So if these are my sorry. Okay, so if these are my assumptions, then this cos del delta becomes 1 and this sine del delta becomes del delta. So incorporating these changes, this is what we have. So for a small del delta, cos del delta is equal to 1 and sin del delta is equal to del delta, the one that we considered. So if we incorporate these two, what we have from the last slide, let's see. So twice h by omega s, we still have twice h by omega s. Then we have d square delta naught by dt square. So we have got d square delta by dt square, twice h by omega s, d square, all these things. Then we have pm. So it will be minus p max into sine delta naught. So p max into sine delta naught minus p max into cos delta naught del delta, minus p max into cos delta naught del delta. So is this expression clear how we got up to this? Is it understood? Okay,
Yes,
I hope
sir.
so. Then what was, yes, any question? Okay. What was our general swing equation? Our general swing equation was twice h by omega s d squared delta by, I mean, this is the equation from where we started. Pm minus p max sin delta. This was our very swing equation. So if this is a general equation, that means this is true for any value of delta. So that means it is true for delta naught as well. So now, can we write this thing from our swing equation, that just instead of delta, we are writing delta naught. So this delta becomes delta naught. So we can write that twice h by omega s d square delta naught by dt is equal to pm minus p max sin delta naught. Can we write this one?
Yes, sir.
So if we can write this one, that means on this side twice h d square delta gets cancelled out with this pm p max sin delta. So all this gets cancelled out. So if all of this gets cancelled out, what are we left with? We are left with twice h by omega s d square del delta by dt square is equal to minus p max cos delta naught del delta. So if I take it on the left hand side, then this is my linearized swing equation. Why is it linear now? I still have a cosinusoidal function. I mean, previously we had sine. We said that because of this particular thing, my swing equation become non-linear. But we still have this cos, but I mean cosinusoidal function. But still we are saying that this is linear. How can we say that?
So delta naught is a constant value.
Very good.
Constant.
So now in this particular swing equation, who is your variable? Your variable is this particular guy, del delta. Del delta. And delta naught is essentially a constant. So cos delta naught will give you a constant value. It will not affect your linearity of your expression. And del delta, which is my variable, that is not inside any sine or cos function. So that's how this equation becomes a linearized swing equation. Clear until this? Okay. So if you have
Sir,
understood up, yes.
why is it important to have a linear equation?
Uh, did you have the concept of poles and zero locations?
Yes, sir.
So the position of poles and zero tells you whether your solution is stable or unstable or marginally stable, right?
Yes, sir. Yes, sir.
But that application or that knowledge is only applicable when your system is linear. If your system is non-linear, then you cannot apply the concept of poles and zeros. So that is what I said in this particular slide. That is that my first target is I have to make my system linear. Once I can make the system linear, then I have to find the characteristic equation of my system. Then I can determine whether my system is stable or not. Is it okay?
Yes, sir.
Good. Fine. So we are done up to this. So let's move forward. Now these are some terminologies that will come in very handy. The term P max cos delta naught represents the slope of the power angle curve at the initial operating point known as the synchronizing power. Okay. So what was the expression of power? Wasn't it something as P max sine delta? This was the expression, right? So if I take the derivative of this expression, then it becomes
Yes.
P max cos delta, this very expression. So if you apply at delta is equal to delta naught, then you end up getting P max cos delta, which is the derivative of PE with respect to delta measured at delta is equal to delta naught. Then this P max cos delta naught is represented as PS, which is known as my synchronizing power coefficient. Okay, you will see that this term synchronizing power coefficient plays a very important part in analyzing the stability of your system. You'll see how. There is nothing to worry. You will see how. So how is it the slope? How did my power curve look like? It looked like something like this, isn't it? So your PS, if you find the slope at this point, then your slope is something like this. If you find the slope at this point, your slope will be something like this. If you find the slope at this point, your slope will be something like this. So all these are my PS evaluated at a specific delta. Say if it is delta 1, if it is delta 2, if it is delta 3. Then say PS1 is di PE at del delta evaluated at delta is equal to delta 1. So similarly, you can evaluate at any value of delta and that will give you your corresponding synchronizing power coefficient. Is it okay up to this? Okay. So in the previous equation, we saw that we had P max cos delta naught. So we concluded that P max cos delta naught can be written as PS. So we simply replace PS and we have now this final expression, that is H by, oh, how did we get pi F naught, by the way? This was, yeah. So we had twice H by omega S. So we had, let me just write. So we had twice H by omega S. So from twice H by omega S, how did we come up with H by pi F naught? Any idea?
So denominator 2 pi f.
Right.
Omega
So
is equal to
numerator is twice H, denominator becomes twice pi F naught. So these two gets cancelled out. So we are left with H by pi F naught. So this is my final expression of the linearized swing equation. So H by pi F naught d square del delta by dt square plus synchronizing power coefficient PS into del delta. So let's move forward. Now,
Sir,
as we
what
said,
does F naught signify?
frequency, whatever frequency you're giving, it will be 50 or 60 hertz based on where you are. Just the frequency. You can keep it as F as well. Doesn't matter. Same thing, all the same. Okay. So now what we do, I mean, this is essentially my characteristic equation. So now in order to go for pole zero location, we need to apply the Laplace transform. There is nothing to worry. I mean, Laplace transform is not that difficult at all. Okay. The only concept that will apply is if you have a d by dt square, sorry, d square by dt square, it is represented as what in Laplace domain?
s square.
S square. Very good. And if you have a d by dt term, it is represented as s.
Yes.
So what we have got h by pi f naught. So h by pi f naught, d square by dt, del delta. So now it becomes s square del delta, but del delta is now a function of s. It is not time dependent or not a function of time. It is now a function of s. Plus ps and del delta is a function of s. Any question until now? This should be clear up till now. Yeah. So from here, what you can do, you can take del delta s common. You can take common and divide del delta s from both sides. Then del delta s gets vanished out. So if it gets vanished out, you are left with s square is equal to minus pi f naught ps by h. Is it okay until now? Fine. So now, if this is your s square, how many solutions will you have?
2.
If this is your
Two
s
solutions.
square, how many?
So 2 solutions.
2
Two
solutions.
solutions. Right. So we will have S1 and S2. And now we'll try to see whether the solutions tell me that whether the system is stable or not. Let's move forward. So case 1, if PS is positive, you see over here, what are the things we have got? We have got pi. So pi is always pi. There is no change in that. F naught is frequency. H is inertia or dependent on mass. So I mean, all these terms, that is pi f naught h, they can never be negative. They will always be positive. Your pi cannot be negative. Your frequency cannot be negative. Your mass cannot be negative, right? But your PS, that is your slope, it can be either positive or negative. So if I take this particular example where we saw, So if I say this is 1, this is 2, and this is 3, all these are 3 PS. So can you tell me which PS is negative?
Sir, number 1 PS is negative.
Number 1, very good. And number 2 and number 3, they are positive. That means what? My PS, that is the synchronizing power coefficient, PS can be either positive or negative. So let us try to see what happens. So if PS is positive, so now tell me, this was the solution. So if PS is positive, your entire solution becomes positive or negative?
Sir, negative if PS is positive.
Right. So if PS is positive, your entire solution remains negative. You see this one. So this is always positive, F naught is always positive, H is always positive. We just concluded that if PS is positive, that means what? If all these terms are positive, there is a minus sign at the beginning. So that means my solution will be negative. So what I can do? For -1, I can introduce a j square. So if I introduce a j square, my solution will be plus minus j root over pi F naught PS. Is it clear up to this, everyone?
Yes, sir.
Okay. Now we know that if we have a S plane, then what do we have in the x-axis? What is there in the x-axis?
Real part.
Real part.
The
Very
real
good. Which is right, which is represented as sigma, right? And what we have
Yes,
in the
sir.
y-axis? What we have in the
The
y-axis?
imaginary part.
How is that written?
J omega.
J omega n. Very good. Okay. So it is written as J omega n. So if you compare our solution S12, then we have got plus minus j. That means what? This root over term is essentially my omega n, which is written exactly over here. So S is given as plus minus j omega n. So my omega n, or this omega n, is also known as our natural frequency. Okay. So natural frequency, this omega n is given by root over pi F naught PS by H. So where will be the location? It will be along the imaginary axis, because your real part is 0, right? So there is no real part in your solution. So if there is no real part in your solution, then plus minus j omega n will lie exactly on this particular imaginary line. So if your solutions lie in this particular axis, then your system is what? Stable, unstable, or marginally stable?
Marginally stable.
Of course, it's written marginally stable. So what would have happened if you had solutions over here? Then your
Sir, it will be
system would have
stable,
been
sir. Completely
very
stable,
good,
sir.
stable. And if it had been over here, then
Sir, unstable.
Unstable.
unstable. Thank you. So now we take the next case, that is PS is negative. So now it is very obvious, if PS is negative, your overall solution becomes positive, because PS is making your overall solution positive. Negative, negative makes it positive. So what is the solution we have? S12 is equal to plus minus root over pi F naught PS by H. So this is my real part only. We don't have any imaginary part. So if it is a real part, then we have got a plus real portion and a negative real portion. So your solution is at a negative real portion and a positive real portion. So now your solution is what? Stable or unstable?
Unstable.
Why? You have got something on the left
Because
of plane as well.
but there is a right side portion as well.
Okay, so say if you had two solutions in the left half plane and one in the right half plane, then your system would have been all of these things you learned in your control system probably. So the question is, if there are more poles on the left half plane in compared to the right half plane, then your solution is what? Stable or unstable? Or sorry, your system is what? Stable or unstable?
So it's still unstable.
Why?
Still
I
unstable.
have got more poles on the left half plane. Why is it
Sir,
unstable?
Sir,
Sir,
there
if
will
there
be
is
an
any
exponential.
Sir, any pole on the right side will result in an unstable system.
There will
Very
be
good.
an,
Right.
sir, there will
It
be ever increasing exponential for
right.
the right hand side.
Very good. So it
So
doesn't
left
matter
সাইডের
if
গুলো
you
ডাই
have
আউট হয়ে গেল, রাইট সাইডের গুলো থাকবে।
থাকবে, right? So even if you have 1,000 poles on the left half plane, doesn't matter if you have even a single pole on the right half plane. So overall, it makes your system unstable. Okay, what does this conclusion help us understand? So what did my power curve look like? It looked like something like this, right? So this was my delta, this was my PE, this was my P max over here. How much was the angle? Can you recall?
So pi by 2.
Very good, pi by 2. So in which half your PS is positive?
So left half.
Left half. That means in this portion, how can I write? Let's take another. Okay. So in this portion, my PS is greater than 0, and in this portion, my PS is less than 0. So if I am on the left side of pi by 2, that is, if my rotor angle is any value from 0 to pi by 2, I can say that my system is marginally stable. And if my rotor angle crosses pi by 2, then I can say that my system is unstable. Is it understood, the conclusion? All right. So moving on. Okay. So I hope you have understood everything until this point.
Sir, it
So
can't be sir, it can't be complete stable at any time. It will be always marginally stable, right?
whatever I have covered until now, your answer is yes. Until now, your system cannot be completely stable. Until now, your system can be at best marginally stable. Okay.
Okay, sir.
So this is what exactly we have. So if your delta angle is less than pi by 2, then we have got a marginally stable system, not stable yet. And if your delta angle or rotor angle is greater than pi by 2, then we have an unstable solution or unstable system. So if you plot, this plotting, I don't know whether it is covered in the lab or not, but somewhere during the course, either in the lab or in the theoretical course, you will see how to make these plots. Okay. These are the solutions in the time domain. So in the S plane, or when you are in the Laplace domain, it is easier to visualize that whether our solution is stable or not. But if you want to plot your solutions and you see in the real time, then it is always better if you come back to the time domain model. So if you come back to the time domain, then we see that this is how your marginally stable system looks like, meaning that, so say initially you are operating at 50 degrees. Okay, so that means what? This is actually your delta naught. So you are operating at a 50-degree rotor angle. Okay, then suddenly some disturbance was there. Because of the disturbance, your system started oscillating. But this oscillation, as you see, it is remaining fixed. It is neither growing with time not decaying with time. So this type of system is known as marginally stable system. Okay, that is a system that is not continuously increasing with time. Also, it is also not decreasing with time, or the oscillation is not decaying with time. So if this is the system, this is known as marginal stable system. And if you have an unstable system, you see, so now delta is operating somewhere at around 130 degrees. Okay, so if it was operating at 130 degrees, and if you apply a small disturbance, you see your system becomes completely unstable. That is, with time, you see, that is a very short time. Okay, just 0.4 seconds. So within a very short period of time, the rotor continuously accelerates, right? That is your d square delta by dt square. So your rotor continuously accelerates, and at a certain point, you will see that your machine will start breaking down. Okay, fine. So all these plots you will do, don't worry, you will do it on your own. Any question until now? If there are no questions, now we'll start damping power. But before this damping power, there are a few things that we need to still, summarize. So let's get back a little bit. I have to start from this particular slide. Okay. Pay attention, okay? Let's see what happens. So when your PM is equal to PE, okay? When this is the condition, then your delta can be written as equal to what? Delta is equal to which particular value, or which particular notation that we used so far?
So delta naught.
Very good. So delta is equal to delta naught. So if PM is equal to PE, that means my generator is running in a stable zone, or it is in stability region. Okay, sorry, in steady state stability. So I can say that my delta is equal to my delta naught. Very good. If omega is my rotor speed. Now say if this is the case, if omega represents rotor speed, then what is the value of omega at this particular situation?
The synchronous speed.
Very good. Synchronous
Synchronous
speed,
speed.
which is my omega
Omega.
s, right? Okay, fine. So we know this scenario. Now, if there is a small disturbance, what are the possible scenarios? Your PM can be greater than PE, or your PM can be less than PE. These are the two possible scenarios that you can have. So let's start with the first one. If PM is greater than PE, what is the relationship between omega and omega s?
Sir, omega is greater than omega s.
Very good. So omega is greater than omega s, and in the next one, it will be omega is less than omega s. Either way, these two situations, what does it mimic? That my omega is not equal to my omega s. These are the two possible scenarios that we have. Okay, so omega s. So this was my synchronous speed, and this was my rotor speed. Did you learn did you learn about any machine where your omega is not equal to your omega s? Anything that you can recall? You have learned something where your rotor speed is not equal to synchronous speed. What do you say to those type of devices? What do you say to those things?
Sir, induction
At-
motor.
Very good.
Induction.
Intentionally, I was trying to avoid the word machine, because if I say machine, it becomes easier to understand that induction motor. Okay, induction machine. Okay, so in induction machine, we saw the scenario where my rotor speed is not equal to my synchronous speed. Okay, so let's see what happened in those cases. Okay, say this was your rotor. Okay, and say this was my stator. So let's talk about induction motor. Okay, not generator. Let's talk about induction motor because it is easier to explain. So these are the three phase. So what you do, you supply your three phase over here. So I supply my three phase over here. There are some conductors within the rotor. Okay, and I mean the coils, and these coils are shorted definitely. So when you supply your three phase, what do you have? Okay, let me take a different color. Okay, when you supply, what do you have in the stator?
So rotating magnetic field.
Very good. So you have got a rotating magnetic field. So when you have a rotating magnetic field within the stator, see, this is your rotor, right? This is your rotor. Your rotor is stand still. Remember, we're talking about motor. We are not talking about generator. We're talking about motor. So these coils, these are shorted somehow, right? I mean, this can be either from the manufacturer or by, I mean, depends on the type of rotor you're using, like squirrel cage or wound cage rotor, all these things, you know. So you have got some conductors. The conductors are shorted, and you have got a rotating magnetic field. So what will happen?
Sir, those rotating
Those
magnetic
coils
field
will sense
ex-
some change
experience
in the flux
in
linkage, right?
magnetic field. Yes, sir.
Yes,
So
they
there
will
will be
sense some
induced
change in the
voltage.
flux linkage or change in the magnetic field. Because of that, I mean, we say that this is induced EMF, right? So that is why the name comes from, right? Induction motor, right? So because of that induced EMF, there will be some currents flow, right?
Yes, sir.
Because the coils are shorted, right? You have got a changing magnetic field. So if you have got a changing magnetic field, I mean, changing the flux linkage and the paths are shorted, definitely there will be some current. That current will definitely start rotating the rotor, right? If that current starts rotating the rotor, tell me what will be the direction of rotation of your rotor?
Sir, in the opposite direction due to Lenz's law.
Before that, what is slip?
Slip is, sir, the difference ns synchronous speed and rotor speed divided by synchronous speed.
Very good. Okay. Okay, you can convert it to percentage if you want, right? So this is the formula for ns minus nr by ns. So initially, when you have RMF, this is your ns, right? This is the cause, isn't it? NS is the cause, right? Do you agree?
Yes, sir.
Okay. And what is the effect?
Sir, the
NR, the rotor rotation. So initially, what is the value of NR?
sir 0.
0. Okay. Now again, I come back to my question, the question that you answered, that because of this rotating magnetic field, there will be a rotation in rotor. We know that there will be some NR. My question is what will be the direction of that NR? According to Lenz's law, the one you already hinted.
Sir, it will hinder its cause of
Right.
cause
Very
of
good. So
this.
it will hinder its cause. That means what? It will try to decrease this difference, right? NS minus NR.
Yes, sir.
So how can it decrease the difference? By rotating in which direction?
Sir, in the same direction.
Right. By rotating in the same direction. Okay.
Yes, sir.
So that means what? Your rotor will also rotate in the same direction and you will start having increased NR, which will ultimately reduce the value of your slip. And all this happens because you have got some windings in your rotor. Is it clear, everyone? What is happening in this particular slide? Any question, please? If you have any question, please ask. But this should be understandable now. If I want to explain further, to explain how it becomes in the same direction, say this is your N, okay? If this is your N, say this is your time, okay? So what you have got a rotating magnetic field. So say somewhere over here, this is fixed. There will be no change in that. So this is your NS. I'm trying to plot NR, okay? Let's see, I'm trying to plot NR. So initially my NR is 0. That means initially my NR is 0 over here. So what are the possible scenarios? My NR can go like this or my NR can come like this. So this is, this line, this very line is, if your direction of NR is in opposite of NS, then it will come in the lower direction. But if you come over here, if this is your NR, then are you increasing or decreasing this difference?
Sir, increasing the difference.
Increasing. That means what? You are violating the Lenz's law.
Yes, sir.
Right? So definitely your NR will increase and it will reach at a particular steady state value. So this is your NR and this gap, this is known as your steady state slip. You have covered these things. You should know. I'm just trying to refresh your memory. Is it okay? The Lenz's law, what does it say? It will affect its cause. So NS is the cause, NR is the effect. The effect will be such that it will oppose the cause. Is it understood, everyone?
Yes, sir.
Okay. So if we have understood, now we will see the concept of damping power. Okay. So what does it say? As long as there is a difference in the angular velocity. So whatever we discussed, that was only applicable if my omega s is not is equal to omega r. So as long as there is a difference in the angular velocity between the rotor and the resultant air gap field. So this is nothing but your RMS. Air gap field, induction motor action will take place between them. So this is what we discuss. All this is to say, if this was my stator, okay, let's say it is better if I take this example, and this is my rotor. So my three phase is over here. So if I have some windings over here like this, if I have some windings over here, then if there is a change in omega s and omega r, there is a non-equal relationship between omega s and omega r, then these windings over here or these coils over here will have some change in the flux linkage, and since they are shorted, they will have some current flowing through them. Because of that, this rotation of rotor, the rotor is already rotating, we know that, but omega s is not equal to omega r. These coils, the current will flow through these coils in such a way that it will try to minimize the difference between omega s and omega r according to this particular Lenz's law. Is it okay? So this is what we are saying, that this is known as my damping coils. Okay. Now we are assuming that my dampers are present. Previously, while deriving the swing equation, we assume that there will be no damping effect. That is, the damper coils will not be present. But now we are trying to see the effect. What will happen if we have the presence of damper windings or damper coils? So if I have the damper coils, these damper coils or damper windings will only play its role whenever you have got this particular situation, that is omega s is not equal to omega r. And that will happen when you have got some disturbance. If you are running in the steady state region, let me get back a little bit. If you are running in the steady state region, you can clearly see my omega s is equal to my omega r. So there will be no effect of the dampers. My dampers will remain inactive. They will not conduct anything. Okay, there will be no current because they are not experiencing any type of flux change. Okay, so nothing will happen to them. But if you have either of these situations, then there is a change between omega and omega s. In that case, your damper windings will start conducting current, and the direction of those currents, I mean the torque, okay, the torque of those resultant currents will be such that it will try to oppose the change. It will try to reduce the value of the slip. Is it understood,
Which are
everyone?
the damper windings here?
It is present on the rotors. The construction is not present, I mean not given at this particular point, but it is present within the rotor. Do you remember the construction of this? You had FD and FD dash, FD and FD dash for
Yes, sir,
providing the
yes.
direct axis field, right? So
Yes.
beside FD and FD dash, there is also some dampers present which are not shown in the previous case, but in the similar fashion you can present some dampers over there. Rotor ke pechaye thake, nothing else. Okay, they are just wound around the rotor, nothing complicated. Is it okay?
So what will the damper do here? It will try to minimize the difference.
Right, it will try to, whenever there is a difference between omega s and omega r, I mean if we apply some small disturbance, then there is a change in PM and P, and we saw that if there is a change in PM and P, there is a difference between omega s and omega r. If there is a change in omega s and omega r, that damper coils start conducting the current, and according to the Lenz's law, those currents will have some torque, and that torque will oppose the cause. That is it will try to minimize the difference between omega s and omega r. Is it understood?
Yes, sir.
না বুঝলে জিজ্ঞেস করো আবার. I will try to explain in a different perspective, but you have to understand these things. Okay. So let's say you have understood. Okay. So our torque will be set up on the rotor, tending to minimize the difference between the two angular velocities according to Lenz's law. This torque is known as my damping torque. Okay. Now let's say your synchronous speed is say 1500 RPM. Let's take a scenario. Okay. And there are two cases. At some cases, say NR1 was 1200. Another cases NR2 was 1000. Now tell me, for NR1, say I have got PD1. I mean PD1 and PD represents my damping power, okay, damping power torque. And for NR2, it represents PD2. Can you tell me what is the relationship between PD1 and PD2? Greater, less, equal. What is the relationship?
PD2 is greater than PD1.
PD2 is greater than PD1. Why do you say so? What is your logic behind this?
The deviation is more in NR2.
Very good, right? So the torque, you see, Lenz's law, what does it say? Lenz's law says that our torque will be set up in such a way it will try to minimize the difference. So larger the difference, larger will be your damping torque. Smaller the difference, smaller will be your damping torque. All this is to say that your PD will be exactly proportional to omega s minus omega r. Or to be more specific, it will be the absolute value of omega s minus omega r. Is it understood, everyone, up to this? So that's why your PD1 will be less than my PD2, because you see the difference is only 300 over here, whereas the difference is 500 over here. So if you have got a larger difference, your damping torque will be larger. So if PD is proportional to omega s minus omega. This can be easily written as by taking a damping coefficient. So I can easily take D for removing this proportionality, and omega s minus omega, this is represented by change in delta over time. So we end up getting this particular damping power. Any question until now? Okay. Now, how do you get the value of this particular D? So it says the value of D may be obtained from design data or by test. So there are some specific tests. Okay, so let's not get into there, but there are some specific tests by which you can find the value of D. That is one of the methods. The another method is your manufacturer will provide you the value of D. So these D will be provided in the steady state values or dynamic values. What do you think? My question is, this D will be provided in the steady state values or dynamic values?
Sorry, dynamic
Dynamic
values.
values, sir.
Very good. In the dynamic region, in the dynamic values, you'll find the value of D, because your damping power or your PD will only play its role whenever there are some dynamics, not in the steady state region. Okay. So finally, what we have got PD is equal to D delta by dt. So we have got a new power which is PD. So again, we'll start from the swing equation, because in the early derivation of our swing equation, we considered that there was no damping power, but now we will incorporate the damping power. So this is my swing equation. So if we incorporate the damping power, it becomes PM minus PD minus P. The question is, why is there a minus in front of PD, not a plus? What do you think? Okay, let it remain as a question. I will request you to explore the answer. Okay, this might be an important question as well. Okay, very easy. The answer is quite easy. It is very easy. So let this remain as a question for the time being. Okay, try to answer in the next class, that is on Friday. I will again ask, and let me see if you can come up with the answer or with the explanation why there is a minus in front of PD and not a plus. Okay, so let's do that. All right. So we start from here. So this is now my swing equation, twice H omega s d squared delta by dt squared PM minus PD minus P. Is it linear or non-linear? Linear or non-linear? I can't hear.
Non-linear.
Why non-linear? Why non-linear?
Did not consider the small
We
disturbance
don't
yet.
have the delta yet.
Right. So over here, the variable is delta, and I know that inside PE, I have got a cos delta. Cos delta or sin delta? Sin delta, right? Sorry. Inside P, I know that I have got a sin delta. So if there is a delta, and delta is the only variable over here. So since there is a delta and a sin term over here, within that, within sin term, we have got the delta. So this equation is non-linear. How do you make it linear? So PD can be written as d delta by dt. All other things you already know. Then instead of delta, just write delta naught plus del delta, follow some sine cos relationship and all these things, and finally you will see that you will end up reaching over here. I mean, this is again very easy. The bottom line is d delta by dt. If you linearize, it will become d del delta by dt. Okay, so in the previous one I showed you how to get the linearized swing equation. So you can apply the same methods and you will easily reach this conclusion. There will be nothing complicated over here. Okay, so we have come over here. If you see, we are trying to do the exact same thing. So previously, what did we do? First of all, we found our linearized swing equation, right? This was my linearized swing equation right over here. Sorry. So over here, this was my linearized swing equation. So after finding the linearized swing equation, what did we do? We went to the Laplace domain. We applied the Laplace transform. From the Laplace transform, we tried to find out the solutions. Based on our solutions, we saw the location of the poles. Based on the location of the poles, we concluded whether our system is stable or unstable. So same thing we will do again over here. So again, we see that this is our expression right over here. This is my expression over here. Now, I know that I need to go to the Laplace domain. So it is better if I do just some small tricks before, I mean, some small modification to my expression before we apply the Laplace transform. So what we do, we divide with h by pi f naught on both sides. So what we have, my d square d delta by dt square. This one, I mean, my target is I will make the coefficient of the d square d delta del delta by dt square as 1. So if I want to make the coefficient as 1, then I have to multiply this with pi f naught by h, but this multiplication has to be done throughout the expression. So if I multiply the whole expression, then this one gets cancelled out. So I have got d square del delta by dt square. In the next one, it will be pi f naught d divided by h. Then it will be ps multiplied by pi f naught divided by h del delta. So if I apply the Laplace transform, so what I have, instead of d square by dt square, I will have s square, and instead of d by dt, I will have s. So I have s square over here. Del delta is now a function of s. Then pi f naught d by h into d del delta by dt is s. Del delta is a function of s now, and this will remain as it is, pi f naught psh, only del delta is now a function of s. So now I have got a Laplace equation. Clear until now? Is it okay?
Yes, sir.
So let's move forward. Okay, so from here, what we do? Okay, so again, the same thing. What you can do, you can take del delta s common, so you will have left with s square plus pi f naught d by h into s plus pi f naught ps divided by h is equal to 0. So from here, what we can write, either del delta s is equal to 0 or this entire term is equal to 0. So which one do you think is more logical? This one is 0 or the next one is 0?
So next one is 0.
Why? What about this one? Why this cannot be equal to 0?
Because we have disturbance.
Very good. Good. This can never be equal to 0. Okay. Because this is the very disturbance that you are applying. So if you do not apply this disturbance, I mean, if your del delta s becomes 0, then there is no point studying all these things. If you do not have a disturbance, then there is no point studying in all these equations, all these expressions. The only reason we're studying all these things, because del delta s is not equal to 0. So that means this cannot be equal to 0. So this has to be equal to 0. So that is what we have. That is s square plus pi f dh into s plus pi f naught ps by h is equal to 0. Clear until now? So if you have any question, please ask. Is it okay?
Yes, sir.
Yes, sir.
Okay, fine. Thank you. Here, now we come to the next question. I think this expression is known to all of you. Have you, I mean, did you see this expression before in any of the courses?
Yes,
Yes,
sir.
sir.
Okay. What is this zeta?
So damping ratio,
Very good. What is this omega n?
natural frequency.
Okay. Although all these things are written, but this is something that you covered already. So you know all these things. Okay. So I have got this expression. So I will compare with this expression. So if I compare with this expression, what do I have? I've got s square s square. I mean, this was the main reason. Okay. I mean, this was the main reason why we made the coefficient of d square del delta by dt square as 1, because we want to compare these two equations now. So s square, I have got s square. So I have got twice zeta omega n equal to pi f naught. I mean, if I compare these two expressions, all these things are written, and omega n square is equal to pi f naught ps. So omega n square is equal to pi f naught ps. So from here, you can easily find the value of omega n. Similarly, you have got twice zeta omega n is equal to pi f naught d by h. So from here, you can easily find the value of zeta. I mean, over here, you can just plug in the value of omega n that you already got over here, and you will end up getting this expression. So what I have got the value of omega n, and I have got the value of my zeta. Is it clear how we conclude or how we came up until this portion?
Yes, sir.
Yes, sir.
So let's move forward. Now, typically, my system is always underdamped. I mean, if this is not the case, okay, let's elaborate on this point a little bit. Okay, before that, we need to see how we got this expression now. Can anyone tell me how we got this expression? How your solution becomes minus zeta omega n plus minus j omega n root over 1 minus zeta square? Any idea? Okay, let's come to this. Okay, so let us see how we got over here. Okay, let me write over here. Doesn't this equation look like some, okay, doesn't it look like x square plus bx plus c is equal to 0? Doesn't it look like this?
Yes, sir.
In that case, tell me what is the solution of x12? Do you
Minus
can
b
you
plus
recall?
minus b plus
Yeah.
minus root over b square minus 4ac divided by
Very
2b.
good. B square minus 4ac divided by twice a. Very good. So now if I apply the same formula, so my S12 can be written as what? Compare these two and tell me.
Minus 2 zeta omega n
Minus 2 zeta omega n. Good. Then plus minus, then
root over 4
root
zeta
over
square omega n
hmm,
square. So 4 zeta square omega n square
4 zeta square omega n square.
minus 4
Minus 4
omega
omega
n
n
square
square.
Very good. Minus 4 omega n square divided by
2.
okay 2. So if I continue, I can write minus 2 zeta omega n plus minus. So I can say that if I take common, if I take 4 common out of it, it will come out as 2. So my okay, no, এটা তো plus minus আছে. Okay, so let's do a what can I take as common over here?
so
Sir,
Can I
4
take
omega n
literally
square.
in that
right 4 omega n square can be taken as common, so it becomes zeta square minus 1 divided by 2. So let's keep on going. So it will be minus 2 zeta omega n plus minus. So if I take this outside, it will be what? Twice of omega n root over zeta square minus 1 divided by 2, right?
sir, I think there is a mistake, sir. The twice a in the denominator, it should cover the whole numerator.
This, no?
Yes, sir.
Okay.
Yes, sir.
Okay. So thank you. Okay. So if this is the case, now can I cancel out these 2's? Can I do that?
Yes, sir.
Okay. Then what am I left with? Minus zeta n plus minus omega n root over zeta square minus 1. So that is minus plus minus so if I want to write omega n, and if I want to write as 1 minus zeta square, what can I do?
J দিয়ে multiply.
Sir, there will be j.
Right. So inside there is a j square, so I can take a j outside. So this is equal to minus zeta omega n plus minus j omega n. Sorry, plus minus j into, sorry. What I'm trying to do is, instead of omega n, I will write omega d, where you understand omega n into 1 minus zeta square is equal to omega d. So you get this expression. Is it understood?
Yes, sir.
Yes,
So
sir.
see, this is the exact expression that we have over here. That is minus zeta omega n plus minus j omega n root over 1 minus zeta square. So if omega d is equal to omega n root over 1 minus zeta square, then it becomes minus zeta omega n plus minus j into omega d. So now see, look at this zeta value. If this zeta is greater than 1, then this becomes imaginary, right? The second term becomes imaginary, isn't it?
Yes, sir.
And also 1, if zeta is equal to 1, then this becomes 0. So in real life, actually, most of our systems are underdamped. So if the value of zeta is less than 1, so this portion will always give you a real value as your output. Okay. So finally, I have my solution, that is S12 is equal to minus zeta omega n plus minus j into omega d, where omega d is equal to omega n root over 1 minus zeta square. Is it clear up to this? Because the next thing is very easy actually. Is it clear?
Yes, sir.
Okay, thank you. So let us try and look at a few relationships. So zeta is given as d by 2 root over pi f naught by hps. We saw how these expressions came. All these things are given. So if h increases, so h increases means what? If by default my d2 pi f naught, all these things are constant, okay? My ps can be positive, negative, or it can increase or decrease. So the two variables are h and ps. So keeping ps constant, if h increases, what happens to zeta?
It decreases.
Right, very obvious. It is inversely related, so it decreases. Same, the opposite for decrease. So if h decreases, zeta will increase. Now, if you keep h constant and if you increase ps, again inversely related. So if ps increases, zeta will decrease. If ps decreases, zeta will increase. Now let us come to omega n. Applying the same concept, now we see that h and omega n are again inversely related. So if h increases, omega n will decrease, and if h decreases, omega n will increase. And what is the relationship with ps? It is directly related. So if ps increases, omega n will increase. If ps decreases, omega n will decrease. Any doubt until now? So if there are no questions, now let us come to this particular interesting slide, okay? And I will ask for your attention. We started at how much? We started at 6:30. Okay, we are almost at the end. Probably this is the last slide, okay? So I appreciate your attention so far. So this is the last slide. The next thing I will cover, these things are different. So static-based modeling. So this will be covered in your Friday class. Don't worry. So now, what was our ultimate target? To find whether our system is stable or not, right? That was my ultimate target. So if you recall from previous derivations, if ps is negative, what was the conclusion? If ps is negative, your system is what? Stable or unstable? Let
Sir,
us go back a little
marginally
bit.
stable.
No. I feel so. PS is negative. Look at the case 2. If PS is negative, then your system is
Unstable.
unstable. Okay. So if PS is negative, your system is unstable. If PS is positive, your system is stable. Okay. So now let us come over here. So if PS is negative, then your dampers become don't care. And dampers and zeta are directly related. You can see this one over here. Okay. So dampers and zeta are directly related. Okay. So damper becomes don't care. So if dampers are don't care, zeta becomes don't care. So your roots are plus minus pi f naught ps by h. That is what exactly we saw. And we saw that my roots will be one in the left half plane, another will be in the right half plane, and that makes my system unstable. This is what we saw beforehand. Is it clear until this? Okay. Now we'll
Yes,
see
sir.
3 cases. Okay. When PS is positive, there are total 3 scenarios. First scenario, when PS is positive, if your damper becomes 0. So if damper becomes 0, my zeta also becomes 0. So this is exactly the same thing as this one. Because in this case, we did not consider any damper. So if we did not consider any damper, we can say that my damper is 0. So if my damper is 0, my zeta is also 0. So if both my damper and zeta are 0, then I see that my system is marginal. Sorry, not this one, this one. Sorry. So in these cases, both of these cases, my damper was 0. So if PS is positive and my dampers are 0, zeta is 0, then my system is marginally stable, right? So this is the same thing over here as well. That is, if PS is now positive, my zeta is 0, damper is 0, zeta is 0. These are my roots, and I can see that my system is marginally stable. Clear until this? Is it okay?
Yes, sir.
Yes, sir.
Okay. Now try to see what happens if PS is positive and my D is also positive. Let's get back a little bit. So which is your characteristic equation now? Your characteristic equation is this one. Okay. This is my characteristic equation. So what are my assumptions? My PS is positive. My my PS is positive. My damper is positive, or damping power is positive. Okay. If that is the case, tell me what is zeta? Zeta is positive or negative? So over here, PS, okay, let me erase a little bit. Okay, over here, my PS is positive, my D is positive. Can your pi be negative?
No, sir.
Can F not be negative?
No, sir.
H also cannot be negative. So what happens to zeta? Zeta is positive or negative?
Positive.
So zeta is positive. What happens to omega n? PS is positive. We assumed that my PS is positive. The others cannot be 0. So what happens to omega n?
Positive.
So omega n is also positive. This is what? My real portion or imaginary portion?
Real portion, sir.
Real portion.
Real portion. So same thing, this and this. So zeta is positive, omega is positive. So your real portion is what? Positive or negative?
Negative.
Negative. So this is your sigma, this is your j omega n, okay? Or omega d, whatever you say. So if I want to plot this now, where will the poles be located?
So in the left hand.
Left side.
Left side, because my real portion is negative, so it will come over here, and I have got plus minus j values, so it will be somewhere over here. So if it is in the left half plane, your system is what? Stable or unstable?
Stable, sir.
Stable. So that is the conclusion over here, as you can see. So you see your solutions are now on the left half plane. That makes your system stable. So if there is a disturbance, now you see it gradually decays out, and this is what I believe I discussed in one of the early classes. That is, if you have damping, you will see that your effect of disturbance or your oscillation gradually dies out. That is, it reaches the stability. Can you recall? Did I discuss this thing?
Yes, sir. You said this.
Okay, so here is the explanation, okay, with expressions as well. What is the other scenario? That is, D can be negative, keeping PS positive. So let's analyze again. So let's see what happens. Now PS is positive and D is negative. For some reason, say we are having a negative damping power. For some reason, it can be a lot of things, okay? But say you are having a negative damping power. If you are having a negative damping power, what will happen to zeta? Positive or negative?
Negative.
Negative. What will happen to omega n?
Positive.
Omega n is positive. What happens to this particular term? Now my zeta is negative, omega n is positive. So what happens to this particular term?
Positive.
Positive. So where will your poles be?
Right side.
Right side.
Right side. Very good. So now you see your system becomes completely unstable. But still, since you have got some imaginary part, it will oscillate, but the oscillation will only grow with time. Okay, it will not reach a stable region. All right. So next class we'll start this one, that is state space modeling for simple RLC circuit, because this is something you people are familiar with. So state space modeling might be a new topic for you, but you are familiar with RLC circuit. So we'll start with this, and then we'll apply the state space modeling in our system. Okay, and we'll conclude our syllabus. So any question in today's
Sir,
class up till now?
Sir, I have a question regarding the
Mhm.
quiz. There is
Oh, acha
this
other
one
quiz
example.
pore. Wait, we'll talk about quiz later. First of all, tell me, do you have any question regarding today's lecture? Any question? All right. So if you don't have any question, let me stop sharing. Also, let me stop the recording. Okay, let me pause it for